if you need help with your lab report, making this video for you. So in our lab, the main point of the lab was to make a connection between the colors of these solutions of ions. These are all metal ions, cations, and their electron configuration. That was at the core of this lab, this experiment, this phenomena. All right, so is there a connection? Well, let's write the electron configurations first. That's what we had you do in your pre-lab. So these are the 6 cations, and I'm going to use this alpha filling chart, and I'll just kind of toggle between that and the periodic table. Now it's preferred that you know how to fill using the periodic table. I'm going to start here and then. So iron is number 26. So I'm going to show you what iron looks like before we remove the 3 electrons to make that a cation. Before we remove 3 electrons. Right, so iron, number 26. We're going to configure 26 electrons in this energy diagram. So we've got 2 electrons going into the 1s orbital, and then your 2s orbitals next, and that can hold 2 electrons. And then your 2p orbitals are slightly higher in energy. If you put these right above it, that's fine too. I'm try to save a little space so I don't run out of room on the top. All right, so I'm there. My next orbital is 3s, and then 3p. And then 4s. And then finally, we're going to stop here at 3d. All right, so that's what iron looks like. And I know I stop at the 6th spot. I know I'm going to have 6 electrons in the 3d orbital because this is your 3d block. And iron is 1, 2, 3, 4, 5. It's the 6th spot in that D block. All right. So the rule is when you're filling atoms, you're going to fill using Aufbau's rule, which is just basically says follow the periodic table. But when you're removing electrons, which we have to do to get positive cations, we have to remove from the highest end first. That usually means the S's before the D's. All right, so I'm going to remove both of those, and then I need to remove one more. Now I can't remove that one because then I'll violate Hund's rule. And I can't remove this one because same thing, I'll be violating Hund's rule. So I need to remove this one, and then the remaining 5 electrons have parallel spin. So that's what I wanted you to show. I'll do one more. Now silver is an exception, so I'll do that. No, that's kind of going to take me a while. I'll do copper. And this time I'll just use the periodic table because my my Aufbau filling chart is gone. So copper is number 29 on the periodic table, so it's over here. And when I say it's an exception to Aufbau's principle, that's, I'll show you when we get there. So let's configure 29 electrons. Give me a little bit more space. Right, the first 2 electrons are going to go into your 1s. So that's represented here. There's your 1s1, 1s2. This is your S block. All right, so I'm going to go through the 2s, and then I'm going to go through the 2p. This is your P block. All right, 2s, 2p. All right, you know 3s is next, but I'm just going to show you on the periodic table. This is the third energy level, and this is your S block. So I'm going to go through that, and then I'm going to go through the 3p. Now, where do we go after 3p? Is it 3d? Well, if you follow your periodic table, this is the D block. We can't skip these guys. All right, so this is your 4s. It's in the fourth row of the periodic table. This is your 4s section there. All right, and then this is your first D block. Your first one available is in the third energy level, so this is your 3d right there. All right, and because copper is in the 9th spot, okay, this is the 9th spot, that's going to be D9. All right, silver is going to end up in 5d9, and gold is going to end up in 6d9. Okay, but we're doing copper. So 4s2, 3d9. All right, so the 4s a little bit lower in energy, and then 3d a little bit higher energy. So what I was saying is this is an exception to the aufbau because that electron is going to get promoted here. Right? So we're filling the entire D sublevel by moving one of the electrons into 4s. Right? So this is what copper looks like. It's an exception to Aufbau's principle. Now, we need to remove 2 electrons to get this 2 positive charge. So where do we remove 2 electrons from? The first one we have to remove from the highest end first. That was one of the points of this lab. Now the second one, it's not going to matter because they all look the same. All right, so here's your electron configuration for copper 2+. Right, so for the 2+ ion, sorry, I forgot to do the electron configuration for the iron 2. I'll do that, iron 3+. I'll do that after. Give myself a little bit more room. So this is all represented by the previous noble gas, which is argon. All right, there's 18 electrons here. 18 electrons, which is argon, which is the electron configuration of argon. All right, so to write the electron configuration of the copper 2+ ion, we can put argon in brackets, and then whatever is remaining. There's nothing here now. The only electrons that are remaining are the 9 electrons in the 3d. All right, so there's your electron configuration for the copper 2+. Now, I copied this from the video that I made. This is had some students come inside to pause my video. All right, so this is what I had. If you, I made the video on doing the lab, so you can watch that if you were absent or if you want a refresher. But the question was on your post lab is, what is the connection between the electron configurations, which is all up here done for you, and then the colors of the solutions, which is summarized in this screenshot. All right, so I can't give you that answer. You've got to make that connection on your own. So if you look at the top 3, I mean, you got to ask yourself, why is there something about the electron configuration that makes this color? And is there something about it has to do with the d-orbitals? The d-orbitals. Is there a reason why the calcium 2 plus ion in solution is clear? Is there a reason why the nickel ion in solution is colored? And it has to do with the d orbitals, the electrons in the d orbitals. So include that in your answer. Now question number 2 is asking, how do we see this color? And what concept have we learned in previous lessons? So question number 2, well, when electrons transition from a higher excited state to a lower ground state, they emit a photon, and that photon has a specific wavelength or frequency or energy. All right, and that's determined by this electronic transition. So the farther it transitions, the greater the frequency, or the smaller the wavelength, or greater than a, the less it transitions, and the inverse of that. Right? So you've got to connect this to your answer to question number 1. And again, it has to do with the d orbitals. Right? So only the solutions, only the cations that have electrons, something like that. You'll notice only those ions are able to produce visible light. Those are the ones that produce color, or that you can see as colored solutions. All right, so you got to use that concept. I think I pretty much gave you the answer. Let me see what question number 3 is asking. Question number 3 is asking, what is the anomaly? What's the weirdo? And I already told you in class that was going to be silver. We confirmed that. Silver is the only one where it has a full d orbitals full of electrons. So it is expected to be clear. But when we added the base, when we added the sodium hydroxide, it turned into a non-white precipitate, where the other ones, the clear ones, turn white, clear ones turn white. And so question number 4 was asking, well, why is that? All right, so the answer number 3 is silver, cation, and number 4 is why. And so if you said something about forming oxides or D sublevel splitting, and I wouldn't expect you to know any of that because we haven't gotten there. So you're looking up answers. The point of number 4 was, look at this. You have 6 electron configurations. Okay, 3 of them produce clear solutions. This one, right? So the calcium 2 plus, the zinc 2 plus, and the silver plus. There's 3. I think you can come up with a reason, one thing that makes this silver cation electron configuration different from the other 2. There's many things you can say, and they're all going to be probably the wrong answer, but the point of this was to get you. I know the answers are online somewhere, so I don't want that. I want you to look at these 3 and interpret something that silver does not have in common with the other 2. All right, it's like, what makes silver different from calcium and zinc? It's basically the question for number 4. All right, number 5, let me copy that. All right, here's number 5. Now, it's asking you to predict which one of these, based off your understanding now, what causes color in a metal ion. Right, it has to do with the d orbitals. Just basically see which one of these matches that pattern. There's going to be 2 of these that have their d orbitals full, and there's going to be 2 that have them partially full. So you don't have to draw energy diagrams for all of these. You can go into your electron configuration condensed mode. So chromium 3 plus on your periodic table, It's right here. So you needed that thing, you know, is going to, the normal thing, this happens to be an exception too, but look here. Chromium's electron configuration is going to be argon, right, plus this here is the 4s, 2, and then the 3d4. Now this is actually an exception, but it doesn't matter because you're removing three electrons. Okay, so if we were to remove 3 electrons from here, again, you got to remove the highest end first. So these guys are gone. Those 2 are gone. And then you've got to remove one of those. So your answer is going to be 3d3. All right, so there's your electron configuration for the chromium 3 plus cation. Now you can see that has a partially full d orbital. If you match that up with the other electron configurations, the other cations that have partially full d orbitals, like this one, they're not full and they're not empty. They're partially full. Well, what do you know? They all have color. Okay, so I gave you the answer to one of them. You'll have to find the other one. All right, so we would expect chromium cation in solution to have some kind of color. Some of you said violet, green. How would you know that without looking it up? I don't want you looking this up. All right, and the reason is because related to the d orbitals. All right, there's one more from the remaining 3. I think you got it from here. If you have any questions, let me know.